Right, so in your previous class, you have learned about the world of real numbers and you have also encountered irrational numbers. Now, in this chapter on real numbers, we are going to continue our discussion and understand two very important properties of the positive integers. So, this chapter mainly focuses on two key topics. The first one is Euclid's division algorithm, and the second one is fundamental theorem of arithmetic. Now, if we look at the name Euclid's division algorithm, as the name suggests, it has to do with divisibility of integers. Let's just write that down. So, Euclid's division algorithm so it has to do with the divisibility of integers. And in simple words, what it says is that if any positive integer a can be divided by another integer b in such a way that it leaves a remainder r that is smaller than b, and that's pretty much it. Now, in a way, it's just to do with the division of integers, right? You probably already recognize this as the long division process. Now, this result seems quite easy and to state as well as understand, but it has many applications related to the divisibility property of integers. We will be touching a few of those properties in this chapter, and one of the key things that you will learn is how do you use Euclid's division algorithm to compute HCF of two positive integers. Okay, now if we look at the fundamental theorem of arithmetic, this has something to do with multiplication of integers. So okay, it has to do with multiplication of integers. Now, you already know that every composite number it can be expressed as a product of primes in a unique way. And this is kind of the important fact, is also known as the fundamental theorem of arithmetic. Now, this is a result that is easy to state and understand, but it has some very deep and significant applications in the field of mathematics. Now, in this chapter, we are going to use the fundamental theorem of arithmetic for two main applications. First is to prove the irrationality of some of the numbers that you have already studied, right? So, it's to prove irrationality of some numbers. Now, what are examples would be square root of 2, square root of 3, square root of 5, and so on. Now, these are all irrational numbers, right? So we just need to prove why they are irrational. The second application of this fundamental theorem of arithmetic, what we are going to look at is when is the decimal expansion of a rational number, let's say p by q, okay, where the denominator is not equal to 0, is terminating and non-terminating, right? So this is what we are finding, terminating as well as non-terminating. Now you know what is terminating. So when p by q, you get a very specific answer that's terminating. Non-terminating is the number kind of keeps on going when you keep on dividing. That is, it doesn't converge, right? So that's what we mean by the non-terminating. And what we are going to, the fundamental approach we are going to look at is actually looking at the prime factorization of the denominator q. And the fundamental idea to remember is the prime factorization of q, this denominator q, is what will reveal the nature of the decimal expansion of this whole whole division of p by q. So that's it in summary, what we are going to learn in this chapter.